Hello everybody, sorry I'm a couple of minutes late, I was just sorting out a few things. So tonight, this live stream is kind of in two parts. The first part is up until 8 o'clock. I'm going to be looking at GCSE content, ideally suited to anybody who's got paper 2 at GCSE coming up next week. And then from 8 o'clock I'm going to be doing some A-level stuff, really for all of those who've got paper 2 tomorrow. And I guess, yeah, that is basically the plan for the stream tonight. Now, the first question I'm going to start with is this one over here. So, yeah. Yeah, people loving the title. Okay, it's a new word I learned this year. Everybody's cooked, it seems, especially the OCR crowd. Anyway, yeah, so let's start with some... Oh, have I done the chat wrong, have I? Oh, did I mess up the your? Oh, do you know what? Yeah, what is the title of the stream? Yeah, you are cooked. Right, so everybody here, I suspect, or most people will have exams tomorrow. Like I say in the chat all the time, down here I've got A-level stuff from 8 o'clock. So ProStar, yeah, people, Neptune, IDK, was it LDK? Yeah, anyway. Let's do some GCSE just to warm up. If you're A-level people, just keep me on in the background. A lot of this you should know anyway. You've probably been assessed this in paper 1. So let's just start with this question here. This is from one of my practice papers I've made that you can buy in my online shop. So go and have a look there. A student is investigating how the extension of a rubber band varies as the force applied is increased. And here we have some data. So we've got force and extension. Now the first thing to do is they need to plot some data. So the first question is actually completing the graph that's shown here, adding the missing data points and drawing in a line of best fit. So when you get a question like this, I think most of the time at GCSE and A-level, then they tend to kind of realise that there's kind of a bit of a time pressure, and actually they just want to see, can you plot data, can you draw an appropriate line of best fit? So in this case, what you need to do is just plot the data from the table, which is fairly straightforward. And then we have a line that is not a straight line of best fit, and it is not a curved line of best fit. In actual fact, you need to have something that fits the data. And what we see here is as we go up initially, we have this directly proportional relationship between the force and the extension. And as we get to bigger forces, that proportional relationship breaks down. So here we've got a straight line, and then we have a curved line. Okay, so what you need to do is, if you're doing an exam, I would definitely suggest doing this in pencil first of all. And if you know that you're happy with that, maybe then go over in a pen if you're completely sure. Okay, and by the way, I am reading all the comments. I suspect it's going to be quite a big live stream tonight. There's probably 20,000 people. No, probably 40,000 people doing physics paper 2 tomorrow. Yeah, thank you so much for everybody who's loved the stuff I've done so far. Okay, so the first thing, easy marks. The second question then is, the student claims the rubber band obeys Hooke's law for small forces. So this means you need to know what Hooke's law means. And basically Hooke's law says that the force is going to be proportional to the extension, provided it's not gone past the limit of proportionality or the elastic limit. Determine the force at which it no longer obeys Hooke's law. So looking at the graph, we want to find the bit of the graph where it stops being this linear relationship and we have this curved relationship, and I would say somewhere around a force of 3 newtons. But of course, there's always going to be a big margin of error in real exams, because they know that, you know, is it 3.0 or 3.1, 3.2? They often give in the marking guidance kind of quite a range of answers that you can get. The student then repeats, the student repeats the investigation but uses a metal spring. The spring has a greater spring constant, and of course we know that F is equal to KE. Okay, now if you increase the spring constant, that means to get the same extension you need a bigger force. So when you plot it, you get a line that for the same value of extension that we had with the rubber band, the size of the force must be bigger, and therefore you must have a straight line that has a steeper gradient. Okay. Again, of course, we know that F equals KE, so the gradient is equal to the force divided by the extension, and if that gets bigger, then this is a gradient and that must increase as well. Now it doesn't matter exactly where, it's more of like a sketch on the graph. That's basically the line there, and we can see that to show how the extension of the spring could vary to an applied force of 7 newtons, assuming the spring does not exceed its limit of proportionality. So that means it could be any kind of line here, it's just a sketch, but of course if it's not exceeding the limit of proportionality, that spring would be obeying Hooke's law and we'd have a straight line. Okay. Right, okay, sorry, I'm just seeing all the comments. By the way, if you're in the comments, do let me know if you are GCSE people or if you're GCSE people. I guess probably a lot of you aren't here because you've got English tomorrow, but you don't need to revise for that, it's just writing stuff down. Let me know if you're AQA, OCR, EdXL, let me know which exam board you're doing and if you're A-level students or GCSE. And of course, if you are A-level people, 20 minutes time, we're going to really start the A-level part of the stream. Okay, finally, the student completes the experiment a third time with a different spring. They are informed that spring A has a spring constant that's twice as large as spring B. So we can say that Ka is going to be equal to 2 times the spring constant of spring B. Okay, now when they are stretched to the same extension, describe how the energy stored compares to the energy stored from A to B. So let's see what people are doing. Okay, AQA A-level, AQA A-level, EdXL GCSE, nice to have you here. Yeah, loads of people. So, Josh is in the AQA gang for life. Nice to have you here, Josh. Thank you. Right, so the energy stored is equal to a half KE squared. And again, if you're not sure about anything in your exam, you will be given a data and formula sheet. Also, can I just stress for anybody who's going into their physics exam in a week's time, get yourself a protractor. You might need to measure an angle or draw a scale diagram or measure something, maybe with the refraction of light. So make sure in addition to your calculator, you have a protractor as well. So basically for the same extension, we can see that looking at this thing here, the half is going to be constant, the extension's the same, and that means the elastic potential energy stored is going to be proportional to the spring constant. So if you've got something with twice the value of the spring constant, so spring A has twice the spring constant of spring B, that means it's going to store twice as much energy for the same extension. Okay, right. Okay, let's not get political, people. I know there's some political chat in here. Basically, you're not old enough to vote and it's not physics. So please do make sure that you kind of just keep the chat in the live stream based on the kind of stuff that we're doing. Of course, if you do anything offensive, I'll just ban you. Okay, yeah, and it is really good that you engage with stuff, but this isn't necessarily the time and the place. Okay, actually, yeah, Cappy, okay, to be fair, James, I believe in you. You're not like the other people watching the stream. James, I believe in you. Okay, to be fair, a lot of A-level people are old enough to vote. Fair enough, you are 18. Okay, so we then have a question. This one's number 9. This is about the way that electricity is distributed by the national grid. So the national grid is this kind of series of wires that basically allows energy to be transferred from where it's generated, if we're talking about electricity, back to where people need it in houses, in buildings, where there's work taking place, and so on. So, describe and explain the role of the step-up transformer and the step-down transformer in the national grid. So basically, the role of the step-up transformer is to increase the potential difference and decrease the current. And of course, if you're A-level, then this is also something that you need to know if you're doing your paper 2 exam tomorrow. So the step-up transformer, the reason you learn about it is because these increase the potential difference and decrease the current. And this reduces the energy losses in the cables as the energy, because we know that power is equal to I squared R. This means the energy losses are going to be proportional to the current squared. So this is the heating effect of that current. Effectively, when you've got a big current, we've got lots of collisions between the electrons, the charge carriers, and the metal lattice. And if you can reduce the current, that's going to reduce the heating effect, and that means that reduces the power losses. Okay, Then, of course, so basically we have a normal value of V here, a normal value of I. In the power lines, we have a small value of I and a massive potential difference at this point. And of course, the power is equal to VI. So the power is going to be the same amount of energy is being transferred every second. And then we step it back down, back to a more reasonable value of potential difference, so you don't get shocked every time you go near a plug. And it's a reasonable current to allow us to use our household devices. Okay, this is kind of a paper one topic, but the next question goes into a bit more about how transformers work. So my assumption is for GCSE, if you've been asked about it in paper one, it might come up again in paper two. Okay, and of course, that's kind of the reason there why we kind of step it up and then step it back down. Of course, thank you, Farhan. You've done your A-levels last year, but yeah, good luck to everybody. Thank you. Yeah, Michaela Lee says, good night to all of my competition. Everybody in this chat, you are competing for a certain number of grades. And everybody here, although it's great to help each other out, you are in direct competition first thing, or whenever you have your exam tomorrow. Okay, explain how a transformer works. Now, if you're GCSE students, learn this, okay? You need to be able to describe for, quite a few marks how a transformer works. And actually, anybody who's A-level in the chat, you need to know exactly the same thing. It's no more difficult at A-level than it is at GCSE. So let's just do a bit of revision. So basically, an alternating current in the primary coil causes an alternating magnetic field. And if we think about our simple kind of transformer, we have our core here, which is made out of a magnetically soft material. We often laminate it in layers to make it more efficient and reduce eddy currents. You then have your primary coil on this side over here, so that's our primary. And then we have our secondary coil. I'm just going to do it in red. It looks a bit like that. Okay, so that's our secondary. Okay, so an alternating current here is going to cause an alternating magnetic field, which is basically north and south, and then north and south, and the poles flip around. And this core is going to transmit that magnetic field through the center of that secondary coil. So we transfer that into the secondary coil, which then induces a potential difference, or EMF if you're A-level people. And at the secondary coil, the number of, if we have a greater number of turns, that means the potential difference is greater. Okay, I'm afraid I can't do GCSE language. Mitt's toenail. Mitt's toenail, that is a great name. I actually, I did a big race a few weeks ago. I've now got 2 remaining toenails. 7 toenails I've pulled off because they were dead, and I've got 1 big toenail that's kind of black and dying. So yeah, I actually only have basically 3 toenails at the moment. It's pretty horrific to look at my feet, but there we go. Okay, and yeah, I was pretty cooked after 100 miles. I don't know. Should I show my toes? I've got I'm in my office, so I'm kind of in bare feet at the moment. So I could show my feet. Maybe people would pay for that. Who knows? Show my feet. I don't know. Shall we do this? Okay, right. So this is my toenail. You can see that one there is kind of dead. This one came off the other day. That one came off the other day. That one came off the other day, and that one came off a couple of weeks ago. So there's basically no toenails. It's just the bed there. So yeah, there we go. And I'm sure that this big toenail here is going to come off quite soon. Anyway, yeah, getting a bit distracted there. Anyway, I'm doing a marathon this weekend, so we'll see what happens after another 26 miles of stuff. And people didn't want that to happen. Okay, right, let's get back to the physics. The next question, we've got a step-up transformer. Anytime you get a question like this, I would say you need to write down next to the numbers what's what. So this means that 100 turns on the primary, this is going to be NP. So put it by that number. When the PD across it is 12 volts, so that's VP. It has a current of 2.5 amps through it, so that's IP. So what we've done here is I've identified the numbers and I've written what's what. Okay. The output potential difference is measured as 144 volts. So this is going to be our output potential difference. And of course, we like to assume that things are 100% efficient at GCSE. So calculate the number of turns on the secondary coil and the current through it. So there are two equations we need to look at. The first one is basically saying that the ratio of the turns, NP over NS, is going to be the same as the ratio of the potential differences. So VP over VS equals NP over NS. Now you can put the numbers in, or you can rearrange it. And I've said the number of turns on the secondary, this one here, I basically brought NS up here, VS up there, and VP down there, is equal to NP VS over VP. So 100 times 144 over 12 is equal to 1,200. And then, once you've done that, okay, sorry, I'm just going to, right, it's going to ban a few people. Right, basically the second thing then to do is to make sure you've got the ratios the right way around. Because we know it's a step-up transformer, we know that NS must be bigger than NP, and it goes from 100 to 1,200, so that must be the correct answer. Okay, the next one then is VPIP equals VPIS. This basically says that the power in on the primary is going to be equal to the power out on the secondary. And of course we can rearrange that to say IS equals IP VP over VS. And again, if you're doing triple science in particular, this should all make sense to you. So we've kind of rearranged the equation to make the secondary current the subject to that equation. We know the primary current is 2.5. Then we've got 12 over 144, which is 0.2. And we can see here, the current has gone from 2.5 down to 0.2. So the primary current is bigger than the secondary current, which again is what you'd expect on a step-up transformer. So what we find is that we step up the potential difference and we step down the current. Okay, do you have to show the rearranging? No, you don't. But I've done it just to sort of try and kind of walk you through step by step. The other way you could do it is you could just use the equation that the data book says, which is kind of IS over IP is equal to VP over VS. You could just put the numbers in. So you could say that we don't know IS, but that's equal to 2.5, and that's equal to VP, which is 12.0 over 144. So you could substitute first, do kind of like a small thing. Okay, have I banned people who shouldn't be banned? Okay, yeah. Yeah, basically, okay, basically I'm going to ignore some of the chat. If people are talking about kind of political stuff, I will just ban people, okay? And it's often a little bit more difficult to actually unban people since that's started. Okay, so basically you can substitute and then rearrange. My preferred thing, and especially for those of you at GCSE who are thinking about doing A-level physics, the best thing, in my opinion, is to do the equation, rearrange it, and then put all the numbers in. Okay, right. We've got about 7 minutes left. Okay. Right, the next bit. A perfect black body is a theoretical object scientists use in models and predictions. The first bit is basically a definition of what do we mean in science by a black body. It basically absorbs all the radiation incident upon it, and it's also the perfect emitter of radiation. Now that pretty much came directly from the AQA specification, and therefore it's something. So I was going to ban a few more people. No way. Somebody says, I taught your current physics teacher. That makes me feel so old, but that's awesome. Okay, so basically a black body is a perfect absorber and a perfect emitter. And then you might have seen the shape of these graphs before. So basically we have the intensity, or the amount of energy emitted per second over a certain area, and then we have the wavelength. So if this is the wavelength going up here, and that's increasing, that must mean the frequency is increasing towards this end of the graph here. So we've basically got low frequency, which is low energy, and then we've got high frequency, high energy at this point over here. Explain which of the curves will be recorded from the object with the lowest temperature. Now, if you've got something which is the highest or the lowest, it cannot be the one in the middle. So we've got to get rid of that, okay? If you're not sure, never guess the one in the middle. Nobody does that. You've got to guess for the highest or the lowest. Okay, and it's basically curve C will be the lowest intensity or the lowest temperature because it's got the lowest intensity at all wavelengths and the peak intensity is at a longer wavelength. And also, the area under that graph is going to be lower, so in total it's emitting less energy per second, which means that it's at a lower temperature. So if we talk about the peak wavelength, we can see the peak wavelength for A is somewhere about here, so that's A, and the peak wavelength for C, the wavelength of radiation given off, is over here. Now that's at a longer wavelength and a lower frequency, so that would be maybe red light potentially, and that could be you know, somewhere in the kind of blue part of the spectrum. Okay, right. Where did I get the question paper from, Ivan? I made this myself. So this is one that you can buy if you go to I think it's probably links on my GCSE website. So if you go to gcsephysicsonline.com, you'll find a link to buy this. And I've got basically a whole series of, do I have it down here? I've got a whole series of papers. So this is from one of my past practice papers that I made. There are 6 in total for paper 2. I'm sure it's a bit too late for paper 1 to be honest. But if you want to get paper 2 papers, these are the ones that you can buy. So there's probably 60 more questions. Okay, right, I'm just going to ban a few more people. I think my title tonight on this live stream basically brought out the crazies. Okay, right. Okay, right. What's the point in buying if I'm showing them to you? I want to show you what I offer, but of course when you buy it, you get the question paper, the mark scheme, you get work solutions, and also there's videos over at GCSE Physics Online where I basically talk through everything. Okay, so yeah, what I won't do is ban any more people just at the moment. Michaela Lee, good shout out to you there. Hello, hope you're doing well. Okay, right. Are these t-shirts for sale? No, they're not, but I'm sure you could get one made for a couple of pounds. But yeah, basically I just thought I'd kind of be consistent with my branding, keep it fairly subtle. But yeah, Physics Online, that's the name on YouTube. I'm also on TikTok, although I don't really post many videos. But yeah. Right, so curve C is the lowest temperature curve. The next question is just about ratios, which is kind of a more advanced question you might get in a GCSE paper. So the Earth continually absorbs and emits radiation. And basically, if this is the Earth, it's basically absorbed radiation from the Sun, and then it's emitted it at pretty much the same rate. But the temperature's now been increasing over recent years, and that means, what can we say about the intensity of the radiation emitted by the Earth? I'm going to call that RE, to the radiation absorbed by the Earth. Okay, so for a long time, the radiation emitted was equal to the radiation absorbed. However, recently, the radiation emitted is smaller than the radiation absorbed, and that means some of this energy from the Sun is being transferred to the Earth, and now the Earth is starting to store that. Its internal energy is increasing. And that means RE over RA is going to, because that's smaller than that. Is that right? Sorry. The radiation emitted is smaller than that. So that means RA is bigger than RE. And that means this ratio actually increases. No, sorry. As the temperature of the Earth is increasing, it must be emitting less radiation. Sorry, RE is smaller than RA, and that means RE over RA must be getting smaller. Okay, sorry, that's not so clear in the thing there. Okay, T says, I helped you get from a 4 to a 9. That's awesome to hear. Really, really glad. Hope it all went well. Yeah. The whole physics class is watching for Scarface. Hello, Scarface's class. Hope all of you are doing well. Okay. Right, the polar ice caps are melting due to increased temperatures. and are decreasing in their area every year. Explain how this will affect the total quantity of radiation reflected from the Earth's surface. So basically, white things like the snow and the ice at the poles are good reflectors of infrared radiation. But of course, if we think about the Earth and we think about the area which is actually white, you know, at the two poles, then as that area gets smaller and smaller, there's going to be less of a white surface to actually reflect that radiation. So effectively, as time goes on and we start to melt the polar ice caps, the Earth gets darker, and that means it's a better absorber of infrared radiation, and that means it's going to get hotter and probably at an increasing rate. Okay, so that is the end of the GCSE stream. Now, we're now going to do some stuff for A-level. We're going to have a look at some multiple choice questions. Before we do that, though, I just want to say hello to everybody who is an A-level student. We are about to start it now. Okay, last minute tips for A-level. Basically, you're going to be fine. If you've got this far, you've already done paper 1, and I suspect if that was a little bit tricky for like OCR, then paper 2 must be easier. Okay, hello A-level gang, Light Sergeant. Great to have so many people here. Mr. Bootle. Yeah, there's lots of stuff here. Now, before we begin, if you are an A-level student, you've got paper 2 tomorrow. That is your main focus. Obviously, though, next week or the week after, you've actually got paper 3. Now, if you are an AQA student, you should go to my shop and buy these. What I've done is I've made some extra practice papers. They're called Alpha, Beta, and Gamma. There are 3 of them that you can basically buy as a pack. And in each one, I have extra questions which are like the kind of style of things you might get in the exam. So, of course, in addition to the questions that you can work through, then you can also see that there's a mark scheme and also my work solution. So you can see how a teacher like me would approach something like this. Pumu Penguin, hello again. I recognise your username. Thank you so much for the donation. That is really appreciated. So today, I'm going to dedicate this whole stream to penguins. I've actually got some Lego from other live streams. One of them happens to be a, kind of like a robotic penguin. So this is in celebration of the donation you've just made in the live chat. Thank you so much. Okay, yeah, right. Somebody says, I remind them of their physics teacher that got fired. I'm not going to ask what they did, but is that a compliment? I'm not quite sure. Okay, so all of you need to go to alevelphysicsonline.com. You can go there tonight. You can see hundreds more videos that explain every part of the course that you might find useful. There are also links there to physicsonline.shop, which is my Shopify store, where you can buy these. And basically go there tonight, buy these, download them, and that's going to help you as you prepare for paper 3A if you are doing AQA. But you can also buy stuff that's actually kind of the same questions but in a different package for OCR or EdXL, which again will help you as you go into that last paper. So enough for me trying to sell stuff. Swag Disease, love that name. Thank you so much again for that donation. Really, really appreciate it. Right, now we're going to begin with some multiple choice questions. Now these questions are from an OCR paper. This is an OCR 2019 paper. But of course, a lot of the questions are suitable for everybody doing EdXL and AQA. It's just that I can't show the AQA material due to copyright reasons. So let's just have a go. And now all of you, it might be some revision from paper 1 stuff, but again, and I said this in like my mega streams that I did last week, which was like 3.5 hours long. If you're doing paper 2, they could well ask you questions about the content that comes up in paper 1. So don't forget anything that you've just been assessed on last week. So which law indicates that charge is conserved? Is it Lenz's, Coulomb's, Kirchhoff's law? So Lenz's law is to do with this kind of negative sign if you're looking at the rate of change of EMF. Coulomb's law, that's actually to do with charges, but it's not about charges being conserved. Kirchhoff's first law, C, is the correct answer. This is because the current into and out of a circuit, this is because the current into and out of a junction is the same, and therefore the charge in per second must be equal to the charge out per second, and therefore charge is conserved. So Kirchhoff's first law, the answer is C, which so many people, Jake, Swizzy, Light, Arjun, Benjamin, Poison Bruv. So many people there. I've seen in so many live streams recently. This is like my 31st live stream of this exam season. Right, the next question, when I first saw this, I thought was going to be really tricky, but it's actually super easy. So we've got two uniformly charged spheres separated by a large distance z. What's the correct distance to use when determining the electric force between the charged spheres? So basically, we know that that force is going to be related to the two different charges and the separation of them. But it's the separation of the centre part, okay? So that's basically from that centre to that centre, which is going to be equal to x plus z plus y. So the answer for this is just d, okay? Now, I would say it wouldn't be just this plus that or this plus that, so it definitely can't be the middle two, so you've got a 50-50 choice, and it's actually the distance between the centre of those charged particles. So the answer for that is D. Oh my god, people are so good tonight. Everybody is absolutely on fire. Maybe you're not cooked. Maybe all of you watching this are absolutely fine. Now, this question here has 4 numerical answers. My advice is, if you see a numerical question like this, don't look at the answers, just do the question. So we've got an electric circuit. There's 2 amps, 0.02 amps coming in, 0.06 amps out there. So the current here must be equal to 0.040 amps. Again, Kirchhoff's first law about the conservation of charge. How many electrons pass through point Y in 10 seconds? Okay, so you need your calculators. Jack Bernard. Yeah, we are not cooked. You're going to smash it. Excellent wise words, Jack. Appreciate that. Okay, so how many electrons? Well, the total charge transferred is going to be equal to the current multiplied by the time, which is 0.040 times 10, which is 0.40 coulombs. Okay, now the equation that they don't give you in your data book is that the number of charge carriers is equal to the total charge divided by the charge per charge carrier. So, and for OCR, this is paper 2. For AQA, this is paper 1 stuff. But of course, all of you know this. Right, so this is equal to 0.40 divided by 1.60 times 10 to the minus 19. Let me just check that on the calculator. So 0.4 divided by 1.6 times 10 to the minus 19 is equal to 2.5 times 10 to the 18, which is answer B, which everybody has said so far. So Musafai, Luke, yeah, Thomas. I'm just trying to see, there's so many names. Light Arjun, is that Zayan? Yeah, right. So, honestly, some of the chat, I wish I had somebody else moderating actually, but if there's any teachers watching, do let me know and do help in, if do kind of jump into the chat if you'd like to, if you're a teacher. Right, okay, we now have 2 radio waves. They're emitted in phase. The waves interfere constructively at point Z, and that means the phase difference is going to be 0, and also the path difference is equal to 0 as well. So this distance xz is 16.0, that's 20, so the difference in path length is equal to 4.0 meters. Okay, and of course this difference here, so the difference in that path length must be equal to a whole multiple of the wavelength. So which value of lambda is not possible? A, B, C or D? People are saying C. So yeah, you could have, if lambda was equal to 1, then you just have 4 of those waves to make 4 meters. If lambda was 2, you'd have 2 of those waves, which make 4 meters. And of course, if lambda was 4, then you just have 1 of those, which would be 4 meters. So here, the answer, the odd one out, must be C, which everybody's getting in the chat. Okay. So I'm just going to hide some people. Okay. Right. Okay, fair enough. Okay, I see there's a compliment. So you're, I think people, yeah. The teacher that I remind you of who got him to get fired, he was basically an inspiration. So I really appreciate that. Thank you. Okay, yes, this is not in the AQA exam. This one is also probably OCR-A only, and I found it when I had to read through it about 7:20 tonight. I found this was quite difficult to explain it. So do you reckon the answer is A, B, C or D? So we've got a potential divider circuit, we've got a fixed resistor, and this variable resistor has resistance R. Now, of course, we know that the value of R, let's say, I'm going to call this R. We know that the value of that resistance divided by R is equal to the potential difference across, I'm going to call that VR, over V. Okay, and of course we know that V plus VR is equal to the EMF of that supply. So we could say that VR is equal to the EMF minus V, and if we put this back up here, we can say that RR over R is equal to E minus V over V. Oh yeah, by the way, CFC Ed, thank you so much for the donation. Again, really appreciate that. And again, if anybody else has access to their parents' credit cards, you can, of course, do like super chats and do donations in the chat, which is always appreciated. And of course, your parents, they're investing in your education, I'm sure. Okay, so basically this means then that the value of R is going to be equal to V. So the value of R is going to be equal to V over E minus V times R. Okay, now of course that's constant, but this means that R, we can't say it's proportional to V like you have here, so it can't be this. It must be proportional to V over E minus V, and therefore A, because the V is going to get bigger as R gets bigger, must be the correct answer. So for this one over here, the answer is A. Does that help? Okay. Thomas says, just stolen your mum's credit card. She is fuming. I'm sure she isn't. Thomas, I'm sure your mum will appreciate the £2. Thank you so much. Okay. Right. Number 6, I had a look at this and I couldn't do it. So I'm going to leave that. It was just too hard. If you ever get a question that you can't do, just leave it and move on. It's only a mark and it's not worth the time and the stress trying to do it. Okay, number 7. All of you can answer this. I don't know how many people are watching. Let's have a look. We've got in the chat, apparently, there are 339 people at the moment watching this. So welcome to everybody. It would be amazing if all 339 people liked the video and also had a go at this question here. Which of the following statements is or are correct about electromagnetic waves? So let's see if we get 339 answers. So again, it's great to see so many people's names. So many people are familiar. Jake Parsons, thank you so much for that donation. Appreciate that. That was really nice. Okay, so they can be plane polarized. That's true. They can be refracted and diffracted. That's true. They have the same speed in the vacuum and glass. Is not true because they slow down in glass, which is why we have refraction. So 1 and 2 are correct, and 3 is the incorrect answer. So here the answer must be C. Okay, that's all good. Right, next question. Okay, the electric field strength at a distance of 2 times 10 to the minus 8 from a nucleus is 3.3 times 10 to the 8. So questions like this, a lot of the time, don't look at the numbers if it's numerical, just think about what the question might say. The electric field strength E is going to be equal to 1 over 4 pi epsilon naught D multiplied by Q over R. And we want to know the value of Q. So Q, okay, Ollie, thank you so much, using your mother's credit card. Sorry, Mrs. Hope, your Ollie is doing the right thing. Okay, so Q must be equal to this, E times R times 4 pi epsilon naught. And when you do that, you find that the answer for Q is 1.47 times 10 to the minus 17 coulombs, which is this one up here. So the answer for that is B. Okay, I think these questions are quite straightforward. The numerical ones are multiple choice questions. Don't think of it as a multiple choice question. Think about it as a question that you can work out and then just check your answer. Okay, CFC Ed, I won't ban you, don't worry, you're doing good. Right, the diagram shows 4 magnetic compasses placed at the same distance from point X. Which of the following is most likely to be at point X? So looking at this, if we think about the field, it basically goes around in a circular path in this direction. And then we can use our right hand to be the right hand grasping rule. Is that right? So yeah, so basically X would be a wire going with the current going into the page away from you. My right hand goes around, the kind of grasping nature of it, and therefore this is most likely to be a straight current carrying wire. That's a GCSE question. Super simple, straightforward. Okay, there we go. The right hand grasping rule, basically if this is my thumb and I've got my fingers like this, okay, so these are my fingers. I've actually got nails on my fingers but not my toes. Basically we can use the right hand grasping rule where this is direction of current, and that's conventional current, and this direction here shows the direction of the magnetic field. Okay. Sorry, I just need to ban some people. I don't know, it's difficult to like talk and ban people at the same time. Okay, right. There we go. And basically X is going into the paper. That's conventional current or even magnetic field going away from you. And a dot is it coming towards you. Okay. Right. This question here, when I first did it, I got the wrong answer. So a coil with 500 turns, so that's N. We've got the average cross-sectional area, that's A. The magnetic flux is this thing here, which is phi. The average EMF is 0.75. What's the value of T? So for this one, I would say that what you need to do, again, is just use the equation, Faraday's law, basically saying how the EMF is equal to minus... There's different ways of writing it, but this is the way that I'm going to choose, okay? So the change in time is going to be equal to the change in flux linkage divided by the EMF. Okay, now here the number of turns is 500 and the change in flux linkage is 1.8 times 10 to the minus 4. This isn't the B field, this is actually phi, so you don't need to know about the area. Somebody saying, Munchma Kuchi, working at McDonald's isn't too bad. No, I think it's a good career if you want to do that while you're young and you're, maybe paying your way through university. So don't worry, I'm sure that won't be the only option after you've done your physics exams. Okay, so that's going to be the number of turns times the magnetic flux divided by the EMF, which is 0.75. So that's just 500 times 1.8 times 10 to the minus 4 divided by 0.75, which is 0.12, which is equal to C. That one there is not too bad, is it? Okay. Hi from somebody saying hi from Revishan's revision server. Yeah, he's doing super well. He's such a nice guy, and he is like absolutely dominating. I'm very jealous of the amount that he's done. So, yeah, fair play to Revishan and all the people that he's been working with. Okay, yeah, we've now got the radius of a gold nucleus. So that's the atomic. That's the number of nucleons inside it. We've got the radius. Let's say gold is AU, and that's RAU. We need to work out the volume of a uranium nucleus with 235. So that's the number in 235. Now, of course, we know that there's different ways of writing this. We might use a capital or a lowercase thing. R is equal to R naught A to a third. That's going to be constant. So R over A to a third is going to be a constant value. So we know that the radius of the gold divided by A of the gold is equal to the radius of the uranium divided by this to a third. Okay, so if we want to work out the radius of that uranium nucleus, we just need to multiply the radius of the gold nucleus by AU over AAU to a third. Okay, so that's just going to be equal to 7.3 times 10 to the minus 15 times 235 over 197 all to the power of a third. And that means the radius is equal to 7.74 times 10 to the minus 15 meters. And of course, once you know the radius, we can then work out the volume from 4/3 pi r cubed. Okay, and basically when you do that, we find that the answer is 1.9, and the answer for this is B. So again, this I reckon is an easy question, but it takes a while to do. Where's the equation from? So this equation here, especially if you're doing OCR and AQA, you should know about that. It's relating the radius. I think sometimes OCR, when they do it, they use a lowercase r for r0. Okay, on here. Yeah. Yeah, and Z Physics, actually Swag Disease, had a chat with Z Physics yesterday. He's got some good stuff coming up. So if you're in year 12, we're kind of maybe working on something together. So if anybody out there has been watching Z Physics, yeah, we had a good call yesterday, good chat about maybe a potential future project coming in September. Who knows? Okay, right, so that one there was number 11. Number 12. Okay, I thought this was a difficult question. Now this question is OCR specification A only. Okay, and basically we want to look at the way that X-rays are attenuated. And basically the intensity is going to be equal to the initial intensity times E to minus mu x, okay, plus or multiplied by the attenuation coefficient of the next one. Okay, and we're going to look at effectively the total attenuation coefficient of that. So the intensity is going to be equal to the original intensity, which was whatever that is, multiplied by E to the minus 0.60 times 0.5 minus 0.20 times 0.5. Shocks. Right. Can I sing Jam happy birthday for good luck? Okay, happy birthday to you, Jam. Thank you for that in the chat. By the way, I will read stuff out in the chat if it's intelligent, if it's funny, if I actually manage to see it. And of course, if you donate money, that always helps kind of flag it up in my eyeline. Yeah. Okay, so basically when you do that, you've got 0.6 times 0.5, which is 0.3, and you've got 0.2 times 0.5, which is 0.1. So we're going to have e to the minus 0.4, which is 0.67. Okay, so you multiply the initial intensity by 0.67 to get the intensity as it comes through. And here the answer must be A. I thought that was a difficult question, and it's only specific to OCR-A. Okay, right, the next one. All of you love capacitors, yeah? I think capacitors are good if you like this kind of stuff. So for this question, there's a lot of information. We've got an EMF of 1.5. The time constant, so RC, is equal to 10. The switch is closed at time t equals 0, and at time t, the PD across a resistor is 0.60 volts. Okay. Now, of course, if that's 0.60, then this value here must be 0.90 volts. Okay, and because it's something which is charging up, we can say that the value of the potential difference across this is going to be equal to V0, 1 minus e to the minus t over RC. Okay, so that's the thing we're going to start with. Now the potential difference across it is 0.90 times the original, which is 1.50, multiplied by 1 minus e to the minus t over 10. Okay, so what I've done is I've used the equation for a capacitor which is charging up. Now that means 0.90 is equal to 1.5, so that's 1.5 times 1, take away 1.5 e to the minus 0.10 t, because something divided by 10 is just the same as multiplied by 0.1. And of course, if we bring this over to here and take that from there, we can say that basically 1.50 e to the minus 0.10 t is equal to 1.5 take away 0.9, which is 0.60. And that's why for this one over here, A is the correct answer. I thought that was quite tricky, but a beautiful question. Okay, look at that. Isn't that nice? Okay, we then have a capacitor discharged through a resistor. So it's fully charged at time t equals 0. We've got a time constant. The switch is closed at time 0. The current in a resistor is I. So when you first start discharging a capacitor, we know that that's when we get the maximum current. And over time, the current is going to decrease. So it can't be C or D. Okay. What's the current at time t equals 10 seconds? Well, it's not going to go to 0 because we've got an exponential thing. So initially, we know that 0 can't be the correct answer. In actual fact, at time equals 10 seconds, when the time is equal to the time constant, that's when it's dropped to 37% of its original value, and therefore that's why the answer is B. And finally, we'll do this question here. Joe, thank you so much again for the donation. Really appreciate that. So, the number of turns on 4 ideal iron core transformers A, B, C, and D are shown in the table below. Now, they were tricky. They were like, this wasn't a nice question. It was a nice question, but a poor table. That's the secondary, and that's the primary. Okay. Okay, Light Arjun. Right, first of all, a big shout out to Light Arjun. £10 for the donation, which I really appreciate. But also, I've seen your name in pretty much every single one of these live streams. And I know you're doing CIE, so it's a lot of my live streams are aimed at people in England. But of course, wherever you are in the world doing Cambridge International, the physics is just the physics anyway. So Light Arjun, and obviously everybody else, thank you so much. Okay. Each transformer is connected in turn to an alternating 240 volt supply, which will give the largest output current. So basically, if we look at the turns ratio, NS over NP, that's going to be equal to IP over IS. Okay, so if we look at the ratio of this to that, that's going to be basically 1 to 1. That's going to be a quarter. That's going to be 4, and that's going to be 5. Okay, so which of those is the kind of the ratio that we're talking about? So here, basically, if the number of turns, going from primary to secondary, that's basically 1, that's 4, that's a quarter, and that's a fifth. Okay, so let's go from primary over to secondary. This is basically a 1 to 1. This one goes from 200 down to 50, so that's a step down. And if you step down the number of turns, we step down the potential difference and we step up the current. So here, because that's a step down transformer, B will be the one that has the highest current. Okay, so I reckon that's about it. And I reckon those questions were actually okay. Now, of course, I haven't been able to answer everybody's questions. I did about over probably maybe 10 hours of live streaming over the holidays where I've got some videos which are more specific to AQA, OCR and EdXL. But of course, thank you, Best Mate. Appreciate that donation. Really appreciate that. I appreciate the sentiment in not being able to donate less than £1. For everybody out there, then I would say that all of you, if you don't know it now, it's too late. Okay, Reese's YouTube account, thank you so much for your comment. I've seen you loads of times. I've won the internet. I appreciate that. Light Arjun, oh, you're from the UK, but you do CIE. Okay, that is quite strange, actually. I thought most people doing Cambridge International were not in England. So, okay, fair enough. Okay. Somebody says, can I sit with you in the exam and help you? No, because I'd probably just mess it up with the kind of time pressure and the stress of trying to get it right. But of course, all of you at the moment, don't spend too long revising tonight. There's only so much that you can learn in the next kind of couple of hours. It's important that you basically reflect on the stuff you've done, maybe check over your definitions, because those are easy marks. Maybe have a look at the derivations that you can do, and that's going to just kind of remind you of all the stuff you do know. Thank you to Puma Penguin. I had kind of your penguin here earlier in the stream. So yeah, again, appreciate that donation. Really, really appreciate it. Basically, by now, if you don't know it, it's too late. all you can do is have a good night's rest, make sure that you get up in plenty of time, you know, all the good stuff, have a breakfast, have some water, and then tomorrow it's basically in the hands of the exam board gods. Whatever they give you is what you're going to have to do. And if it's a hard paper, it's going to be hard for everybody else. So if you were doing OCR in particular, you had a hard first paper, don't forget that everybody found it hard, including lots of teachers who've emailed me asking about how do they do certain questions, looking at the language, they found it quite difficult. So basically last minute tips are, if it's hard for you, it's going to be hard for everybody else, and everybody's going to struggle, which in a way is a good thing because it lowers the grade boundaries. But of course, all of you have a huge amount of knowledge from many, many years of doing physics at school. Okay, so I reckon that's about it for the night, really. If there's anything that you need help with, go to alevelphysicsonline.com. You can select your exam board, you can find the topic that you need help with, and I reckon that's going to really help you prepare. If there's anything you're maybe not 100% confident with, just having my soothing voice easing you off to sleep as you're learning a bit more physics could be the difference between that grade C and a grade A. Anyway, I will be back after this. I'll be doing more live streams next week, helping you prepare for paper 3, and I'll see you all in the live streams, if not at some events around in the future. So yeah, thank you so much, and yes, I will be doing paper 3 streams. All of you are going to be absolutely fine. Good night.